Okay, today we're going to talk about angular momentum. We're going to define angular momentum. And it's very similar to linear momentum, so we'll review linear momentum a little bit. So stay up with that. Then we'll define angular momentum. Then we'll talk about conservation of angular momentum. When is angular momentum conserved? And maybe we'll work an example problem. And then I can't do it under the document camera, but we'll do a bunch of demonstrations using chairs and books and stuff. I'm going to spin you guys out of a chair and demonstrate conservation of angular momentum. So anyway, let's get started. Linear momentum, let's review. Linear momentum. Well, how do we get started with linear momentum? All right. Well, it all starts with Newton's second law. That if you apply a net force to an object, that object accelerates, and the amount of acceleration you get depends on how massive it is, how much inertia it has. Well, then we notice, well, what is acceleration? Well, it's the rate at which we change velocity. Now, let's say that we have an object where there's a net force on it, but its mass isn't changing. Okay, the mass is constant with time. So the mass just stays out here. It's the velocity that's changing with time. And so we can say this is mass times the final velocity minus the initial velocity over time. And so I distribute this in. I distribute the mass in here, and we get the final velocity minus mass times the initial velocity over time. And so we add this quantity, mass times velocity, and we define that to be momentum. Or in this case, linear momentum. We used the lowercase p to represent it, and we said this is equal to mass times velocity. And it's a vector, so the momentum vector has the same direction as the velocity of the object. And so we kind of go back and we said, well, the net force is equal to, well, if this is the final momentum and this is the initial momentum, then this is really the change in momentum over the change in time. And this is Newton's second law. This is how Isaac Newton described it. He described a net force as being something applied to an object that's going to change that object's momentum. And there are circumstances where the velocity doesn't change, but the mass is changing with time, and that will be a change in momentum. That's like a water out of a fire hose, and you feel a force from it. So that kind of situation. We don't really deal with those in here. But in any case, now what did this lead to? Well, what if if over a period of time, what if the net force, let me make the notes good. What if the net force equals 0? Well, if the net force is equal to 0, then the change in momentum has to equal 0, right? If you're not applying a net force to a system, then, well, it's net force that changes momentum. So what we're saying is that if there is no net force acting on a system, there will be no change in momentum. Well, this is P final minus P initial, if that equals 0, then we get this situation where the final momentum equals the initial momentum. And we've just kind of redefined, or we just reviewed conservation of linear momentum. Okay, well, now we're going to do an almost identical thing. We can take these notes that we just wrote up here and just substitute variables. Instead of m, I'm going to use iota, right, or I, for rotational inertia. Instead of a, I'm going to use alpha for angular acceleration, and we're going to go through the same set of logical steps. And we'll see that we'll get something very, very similar. So when we take a net torque, we say that net torque equals the rotational inertia of the object times the angular acceleration. We derived that before. If you apply a torque, a net torque, to a system, to an object, or a system of objects, you will change the angular velocity of that object over time. That's what a net torque does. It makes things spin, or it changes the way they spin. If something isn't spinning and you apply a torque to it, it'll start spinning. Or if something is spinning and you just let air friction or friction, if you apply some torque to it, it will stop spinning. I mean, here, I applied a torque to it, right? I've got this little top. I applied a torque that's forced through little distances on right here where my finger, interact with this, and it spins. And we know that this thing's going to come to a stop here because there are other little torques acting on it. There's a little bit of air friction. It's rubbing the paper, where it meets, and it's slowly, and if I want, but this thing spins really for a long time, so if I want to apply a little torque and make it stop. So torques are what change the way things spin. And, well, this is I times, well, how did we define angular acceleration? We said an angular acceleration is a change in angular velocity over a change in time. That's the definition of angular acceleration. Well, this means that I can say this. This is I times the final angular velocity minus the initial angular velocity divided by time. And then, so I can say that the net torque is, well, now I can distribute the rotational inertia into this equation. And, well, now I've got something quite interesting. I've got this product of rotational inertia and angular velocity. And we're going to give that a name. We're going to call that angular momentum. Now, angular momentum, for reasons that, by tradition, convention, that, I don't know, some people thought of decades or maybe a century or two ago, we use a capital L to represent angular momentum. I don't know why. Just when you see a capital L, that's what we use to represent angular momentum. Huh? Ooh, that could be it, because it's like a cross product. I don't know. Yeah, could be. I just think, oh, we haven't used capital L yet. I think that's probably what happened. But who knows? You might be right. All right. So So what we have here is that the net torque on our system, well, this is L final minus L initial up here over time. And so this is so really the net torque is the rate of change of angular momentum. Wow. And I think as we go through this, you might hopefully are getting a little sense of what theoretical physicists do. And that is they say, okay, well, we know this is true. And then they expand quantities out. We know that this is equal to this. And then, oh, well, then this goes, well, oh. So they go through mathematics to derive things. And then they go find out if those mathematics are making correct predictions. So kind of going through the mathematics of this is what theoretical physicists do all day long. It sounds like an exciting job, huh? Well, it's a lot of hard, tedious work. But when you discover something or think of something that no one's ever thought of before, it's quite exciting. And, really cool. Well, what happens if there is no net torque? What if the net torque equals 0? If the net torque equals 0, well, what do you think is going to be true? If this is equal to 0, well, then, like delta t isn't 0. I mean, there's a span of time. First of all, you don't want to divide by 0. But time goes by, so delta t isn't 0. So if the net torque is 0, then delta L has to be 0. Then the change in angular momentum must be equal to 0. In other words, if you are not applying a torque to a system, if there is no net torque on a system, then its angular momentum is not going to change over time. Torque is what changes angular momentum. This product of, oh, I didn't really finish this, did I? L is equal to I times omega. The rotational inertia times the angular velocity. Now this quantity, in other words, so if the net torque equals 0, then angular momentum doesn't change over time. Angular momentum is conserved. And this is among the most profound ideas in physics. These conservation laws, I mean, we have 3 basic conservation laws now that we can use to understand the universe and solve problems and create technology. One of them is conservation of mechanical energy. That is, if the only forces doing work are conservative forces, then mechanical energy will be conserved. In a larger sense, energy is always conserved if you include internal energy, heating, vibration of molecules, that sort of thing. And then we had linear momentum. If there's no net force acting on a system, like in a collision or something like that, where the forces are all internal to the system, and for every force on one object, there's an equal and opposite force on another object, so therefore there's no net force on your system. The individual particles in your system, they might change their momentum, but when you add up all the changes of momentum in your system, it will equal 0. There's no change in momentum overall for the whole system. Same is true here. If you have a system of rotating objects, and you measure their angular momentum. If there's no net torque, then this will be true. I omega initial will equal I omega final. And we can use, if you see a problem where there's no net torque on a system and it's spinning, but you might have two things spinning that come together and connect, and you want to know how they're spinning afterwards. It's kind of like a rotational collision right here. But the most interesting and common things you'll see is, this product here, like the way I wrote this product right here, it implies that I is a constant, right? Well, what if you had a system where the rotational inertia, or iota, I should say, what if the rotational inertia changes? Then, then I really should express it like this. The initial rotational inertia times the initial angular velocity will be equal to the final rotational inertia times the final angular velocity. And so this is one we're going to use a lot for the kind of problems that we're going to be doing. So I think this kind of concludes the lecture part of it in terms of like the concepts and the materials. Oh, let's take a quick look at units though. What are the units for angular momentum? Well, what are the units for rotational inertia? Kilogram meter squared. And what are the units for angular velocity?
Radians per second.
Yep. Sometimes they'll include the radian, sometimes they won't. And actually, this expression does work. I think it works for revolutions and so on, but I think when you're dealing with torque and when you're dealing with angular momentum, I think we just stick with radians. Stick with radians because you're almost always going to have some kind of torque involved at some point, and so you don't want to mess around with revolutions or degrees. Nobody really uses degrees per second, right? I've only seen radians per second or revolutions per second or revolutions per minute. So, but these are the units for angular momentum. All right, let me zoom out. And just the last thing I want to show you, I mean, I don't know if I can get both of these, but notice that mathematically, we went through the same basic mathematics to define linear momentum, and when linear momentum is conserved, as we did, angular momentum. And that's kind of beautiful. I mean, this is what when physicists take aesthetic pleasure from the universe, when they see things like this, little symmetries, little things that work the same way, little patterns, they get kind of excited. They think this is cool stuff. And it is cool stuff. I don't know. Yes, Megan. Yes.
You guys are just kind of dorky.
Dorky? Let me tell you something. It's a good thing there are dorks in the universe, in the human population, because without it, we'd all be living in caves. All right. Not that there's anything wrong with caves. All right. That is